Sirisha ma'am, Subbarao sir has joined.
Oh, okay, Sandeep. Yeah.
Yeah.
So we welcome you, sir. Yeah.
In fact, I joined a couple of minutes earlier, okay, but with the wrong name.
Oh, okay.
Sir, I have given you co-host permission. You can share your screen, sir.
Sir, 1 second, I'll be back.
Yes, sir.
Okay, the call is from your college only, just to remind them about the meeting. Okay.
Okay, sir. Okay. Shall we wait for 5 more minutes and start the session, sir?
It's
I'll
okay.
just,
It's
yeah.
okay, madam. Who are the participants? Shall I have a feel of that? Are
Yes.
they faculty from other colleges or your college or students?
Yes, sir. Faculty, combination of both, sir. Faculty members from various other colleges, as well as from our college also, as well as students also, sir.
Okay, so what's the rough numbers of this mix? Okay, how many are students and how many are faculty?
Sandeep, can you brief it? There
Yes,
are,
ma'am.
I guess, according to my
Ma'am, there are around, sir, there are around 648 students and 124 faculty members.
Participants, there are 700 participants.
Yes, sir.
Okay.
Right now we have 39 participants in Zoom, sir, and
Okay.
YouTube also. This live streaming is going on. There are 6 in YouTube at the moment.
Okay. Can I interact with all, or I
Yes,
can
sir.
only interact with some?
Sir, I have kept the chat window enabled.
Hmm.
If you want, I will keep the mic also on, sir, for the participants.
For Zoom participants, what about YouTube?
So YouTube, they will post in the chat. I will let you know, sir, as they post.
Okay, okay, that's fine.
Yes, sir.
Okay, we'll wait for a couple of minutes and then whenever you feel like
Yes,
it's time to start, we'll start.
okay, thank you.
yes, sir.
Hello, Sandeep. We should start now, okay? Yeah. Respected speaker, Dr. Subbarao Garu, faculty members from various colleges, my dear colleagues and students, a very good afternoon to one and all. I, Sirisha Careless, Assistant Professor in CSE Department, feel privileged to welcome you all on behalf of Organizing Committee of KMIT for this one-week online workshop on privacy and cybersecurity. In today's session, let us have an overview of blockchain technology. Dear all, have you ever wondered why blockchain is important? Or maybe you have asked how is it going to impact our daily life or the lives of different professionals working in different sectors? Yes, in few words, a blockchain is a digital, ever-growing list of data records. Such a list is comprised of many blocks of data, which are organized in chronological order and are linked, secured by cryptographic proofs. With this brief note, I am delighted to have the gracious presence of our today's resource person, Dr. Y.B. Subbarao Garu, Associate Professor, School of CIS, University of Hyderabad. Dr. Y.B. Subbarao Garu has completed his MTech from ISI Kolkata and PhD from University of Hyderabad. He has published various papers on security-related issues in various journals. Sir, it's an honor to welcome you on behalf of organizing team of KMIT. Without any further delay, I would like to hand over the session to Dr. Subbarao Garu. Over to you, sir. The board is all yours.
Let me first thank the organizers for giving me this opportunity. Okay. Today I'll be briefing you about blockchain technology with the help of Bitcoin as a case study. Right. How many of you are already aware of blockchain? Is there a way for you to respond? Those on Zoom, you can respond probably. What's your awareness on blockchain? I've been giving this introduction almost for past couple of years. When I started this activity, okay, very few people do know what blockchain means, but these days I feel it's relatively well-known concept. Okay, before I start my presentation, let me have a feel of what's going on with my participants. Please, anyone can respond if possible. Yeah, there are already some chat responses. It's a distribution chain. And one person said that he is aware of BCT. Okay. Okay. The messages can be typed to all also. Okay, even if it is direct, it's fine. No issues with that. Any more responses? One second, just give me a couple of minutes time. I'm just looking for your responses. Okay, we'll start. Okay, is my screen visible to all of you?
Yes,
What are your
sir.
thoughts, friends?
Yes, sir.
Yes,
It's
sir.
visible.
Okay, so you can see my email ID there. Okay, those of you who wanted to ask me any questions at a later point can note it down. Right? As I said, I'll be talking about blockchains with Bitcoin as case study. One second. Yeah. In general, people believe Bitcoin and blockchain mean one and same, but it's not the reality. Okay. Bitcoin is an application of blockchain technology. Okay. Blockchain as such is a new technology which was suggested by Satoshi Nakamoto. Okay, but I mean, nobody knows him as a person. Okay, it can be a person or it can be a group of people who themselves called as that name. Okay, but this happened in 2008 and they suggested the technology with the application that we are looking at today. Okay, that's Bitcoin. Okay, what is meant by Bitcoin? You might have seen the same name uh, everywhere around you, or you might have come across another term for that, cryptocurrency. Okay. Again, what is meant by cryptocurrency? What is currency in general? Okay. I mean, this is really a tough problem for me talking to you without seeing you personally, right? But we can't help it. Currency, by definition of currency, it's backed by some regional government, okay, around regional administration, right? Unless any currency is backed by regional government, you can't call it as currency. Okay, say for instance, rupee is Indian currency, dollar is American currency, like that. Okay, then what is cryptocurrency? In real terms, okay, it's not really clear whether you can call Bitcoin as a currency or not. Okay, because Bitcoin is not backed by any government as such. Okay, anyway, these are legal aspects related to Bitcoin. I don't want to spend my time with that now. Okay, we'll go ahead with our technical stuff, right? We'll understand what is meant by Bitcoin in a phased manner, right? You can deal with Bitcoin in the same way as you deal with your currency. That's why people prefer to call it as cryptocurrency. Okay, you can use your rupees to buy some groceries, to buy some equipment that you want to, whatever purchases you want to do, you can do that with your rupees. And how your rupees are dealt with, okay, in hard form as paper currency, and also in digital form through your banks or other wallets that you use daily, right? Bitcoin transactions can also be done in similar way, okay, to your wallets. Okay, you can't really see Bitcoin as a physical currency; it's only digital currency, right? That's why that name cryptocurrency comes into role play. Okay, and in yesterday's budget, you might have come across Indian government's willingness to come up with its own digital rupee. Okay, what it means, we'll not talk about that today. Okay, but end of the talk, you can figure it out yourself. Okay, that will not be so difficult for you to understand, right? We'll talk only about Bitcoin as a cryptocurrency, right? Okay, and the usage of Bitcoin cryptocurrency is almost similar to your any wallet which you use to spend your or use your rupees. Okay. What are various wallets that you know, like Paytm, Google Pay, many other wallets? Okay. Day in and day out, every one of us will be using them, okay, because that became a prominent tool for us after the demonetization, right? Okay. Bitcoin is exactly similar to that usage. Okay, you may have various wallets for Bitcoin using also, right? Many of them you will be seeing in TV advertisements also in these days, right? You can download any such wallet and start accumulating Bitcoins for yourself and start spending them also the way you want to spend. Okay, but Bitcoin, the value of one Bitcoin is real, almost close to 5 lakhs or much more than that. Okay, close to 35 lakhs if I'm not wrong. Right. Bitcoin is really an very valued cryptocurrency for that matter. But there are many other cryptocurrencies. To understand what is meant by cryptocurrency, we fix our focus to Bitcoins. Fine. As many of you were rightly visualizing, okay, a blockchain means decentralized computation, and it's also information sharing platform that enables multiple authoritative domains. Okay, important point here is these domains will not trust each other. Okay, but they still cooperate, coordinate, and collaborate in rational decision making. Right. So it's also a public ledger. Okay, the ledger which is available publicly. What's meant by ledger? A record book which records everything. Okay, and this is digital ledger which is publicly available, right? And in which all committed transactions are stored in chain of blocks. Okay, see the image here shows you as block 1, block 2, block 3, and so on, where these blocks are chained together. Okay, in reality it's not a physical chain like this. The linking happens through some cryptographic function. Okay, what's it? We'll see very shortly. Yeah. These are the building blocks of blockchain as technology, right? Okay, these cryptographic tools play together, okay, and gives us an important and interesting technology which interests us today, which is called blockchain, right? These tools are hash function, digital signatures, public key. In fact, it's not public key infrastructure; it's public key encryption system, right? Which gives us digital signatures also, right? And Merkle tree, okay, is yet another concept, and this is not really cryptographic component, but still an important tool in blockchain, which is called as consensus. Right? There are different consensus algorithms about each. We can spend some time and understand. Okay, because Bitcoin uses a particular consensus algorithm, we'll focus more on that. Okay. Let us go one after another. Okay, but please, these tools are actually from cryptography. I will not be really spending my time in detailing about the cryptographic character, right? We'll very briefly see what each of this means, right? As the title says, okay, we are trying to give an overview of blockchain. Okay, it's not the detailed explanation. Okay, what is meant by hash function? Okay. You know, any function maps a domain to range. Okay, you all know, you learned it from your high school maths, right? In particular, this cryptographic hash function maps very large domain. Okay, I mean any possible binary string of any length to binary strings of fixed length, right? Okay, such functions are called hash functions. Okay, which map large domain to a small finite range, right? Okay, here our domain is bit strings of any length, right? And our range is just an n-bit string, right? Okay, in particular in cryptographic hash function, we'll be fixing this n as 256. And this hash function should have some basic security properties. Okay, one among them is collision resistance. What is meant by collision resistance? Picking two different strings from your domain. Okay, I mean 2-bit strings where both map to same hash value. H of x is equal to h of y. You have to pick two strings x and y such that you get hash value h of x is equal to h of y. Okay, if such a choosing is possible, if such picking is easily possible, then your function is not collision resistance, right? But we want collision resistant hash function. Means nobody could be easily pick such x and y which map to same hash value, right? This is our first requirement, right? They resist collision. Your hash function must resist collision. Collision should not occur so easily. Okay, good. Next. Next property is hiding, and another property is puzzle friendliness. In reality, I mean, in application, we are interested in puzzle friendliness. Okay, I'll explain this very quickly. Okay, both are almost similar. Okay, let's not worry too much about how to differentiate these two properties. Right. See, let me read this definition for you. Hash function h is said to be puzzle friendly if for every possible n-bit output value y, if k is chosen with high min entropy. Okay, don't worry about what is meant by high min entropy. Okay, with randomness. Okay, just take the word randomness. Right? You are given the knowledge of k which comes randomly from your domain, right? And your hash function acts upon this random string k which is concatenated to a small string x, right? And the output of this concatenated input is y. Okay, you are given the values y and also k which comes randomly from your domain space, right? But you don't know what x is, right? And computing this x, okay, is not so easy to do, and you can't do it in any time which is significantly lesser than 2 power n, right? Okay, that's what you call puzzle friendliness, right? Okay, where n is the length of your output y. Okay, so you have to try with all possible combinations, only then you will be picking up an x, right? And this kind of thing is not going to be so easy. Okay, this is an important requirement for blockchain technology as such, and in particular bitcoins also. Okay, I'll be demonstrating this when I really explain the blockchain, I mean bitcoin as a technology, right? Okay, but this property of hash function where you know y and k, but still calculating or computing x, you can't do it in any time which is significantly lesser than 2 power n, right? This is written as infeasible to find x such that the time is less than 2 power n, right? Okay, so this property helps you a lot in your application of blockchain technology. Okay, right. Now, what is meant by digital signatures? I hope you all know a bit of cryptography, right? Okay, and if necessary, and if there is any time left, I can spend a few of my minutes towards my end to talk about a little bit of cryptography. Okay, but I believe we are all aware of basic cryptographic tools. right? And in cryptography, there is a particular thing called public key system, right? Okay, let me very quickly, for those who don't know what is cryptography, for those people, let me very quickly explain what is meant by public key cryptography. Okay, say, I mean, this is not technical explanation. This is only a heuristic idea of what is meant by public key. Okay, if you say two people stay in your home, okay, you and your brother, okay, only you two people stay at your home, right? And you have different working times, right? So how both of you will access your main door of your home? Okay, you will have one lock with two copies of keys for the lock, right? You will have one key with you and one another key will be with your brother, so that any of you can lock or unlock the door, okay, with your respective keys. Am I right? Okay. Here, the locking or unlocking key with both of you are exactly same. Okay. If you want to go out when your brother is not at home, you will simply lock it. Okay. And when your brother comes back, he'll unlock it. But copies of the key that is with both of you is exactly same. Okay. 1 second. Amma cheppam. Okay. Okay. Thanks. I'll take it. Yeah. Yeah. Hello, listeners. Just excuse me for a couple of seconds. Okay, I'll just change my presentation. Just. Yeah. Is my presentation visible?
Yes, sir.
Yes, sir.
Okay. I mean, this will contain the same content. Okay, just for some technical reasons, I'm just changing it. Yeah. So we are at this particular slide, right? So I'm talking about the way you and your brother can lock your home, right? But when it comes to some place like a temple hundi, okay, how can you drop money? Anybody can go to the hundi and they can take their money from their pocket and just drop it into the hundi through the small hole which is there. Okay, but can you take out the money also in the same way? No, to take out, I mean, to open the hundi, you need some other key. Okay, so public key encryption is such a mechanism, right? To send a message, say to a banking system, okay, assume to the bank itself. right? To send a message to the bank, all that you need is public key of the bank, okay, which can be known to everyone, right? But to receive the message, okay, bank will be having a secret key for itself, right? Here, the locking key, which is the encrypting key, right, and unlocking key, which the bank has, that is the secret key, are two different keys. They are not same. Okay, so this difference one has to understand. Okay, locking key and unlocking key in public key system are two different keys, right? So that's why the first line shows there are three algorithms. Those three algorithms, first algorithm is generate keys, okay, which generates two keys, secret key and public key, sk and pk, right? And signature is done by the secret key, which only the owner of the system will be knowing, right? Whereas verification of the signature can be done by anyone who has the signature along with the message and also the public key. Public key is known to everyone, and the message for which the signature is done and signature are given together. Okay, if I want to give some document, a signed document for a verification, that will have my document copy and also my signature. Only then somebody can verify it. Am I right? Okay. So in this public key case scenario, okay, public key is also known to the world to verify my signature with the help of three inputs: public key, message, and signature. It's verified. Okay, this function is called verify function. It will return is valid or is not valid kind of result. Okay. These are the three functions: generate keys, generate the key, secret key and public key. Sign as a function takes input secret key and message and gives the signature of the person owner for the particular message, right? In normal case, when you sign on paper, your signature is fixed, always it is same, right? But in case of digital signatures, your signature depends on message also. For every new message, your signature will be different. Okay, so otherwise digital signatures can be easily copied. This is not the case. Okay, as this is message dependent, people cannot so easily copy your digital signature, right? Okay, many people think just photocopying their signature and pasting it wherever they need is digital signature. No, that's not the case. Okay, digital signature always deals with or uses public key system, and secret key component of that public key system will help you to do digital signatures, right? This is what I want to emphasize at this level, right? And this digital signature system will have two properties for them to hold. Okay, whenever you have a message with proper sign which you got from the message, okay, and a public key, the verification function will return true. Okay, I mean is valid. This means true, right? And these signatures are existentially unforgeable. Means this is again a little tricky cryptographic term. Okay, not even for a given message, even for a random message, okay, the attacker will not be able to sign an unforged document, right? Okay, even for a random document, such a forgery is not possible. That is called existentially unforgeable, right? I don't think I can really make it clear what is meant by signing a random document at this stage, right? Okay, but let's not worry too much about it. Okay, even random strings cannot be digitally signed with such certain public key cryptographic systems. Okay, in particular, your blockchain technologies, that's Bitcoin network, will be using elliptic curve based digital signature system, which is called as ECDSA, right? And it is definitely existentially unforgeable public key system. Okay, that you can believe, right? So digital signature that is used in Bitcoin network is called ECDSA. Okay, A node initiates a transaction in a blockchain network by employing a digital signature. Okay, means what do you mean by this? I'll explain this in a bit more detail. Say, okay, my slides are technical. Okay, you will not have these kind of details there, okay, but let me explain to you. As a user, how will you deal with bitcoins? As I said, you can go to Google Play Store and download any wallet which can deal with bitcoins, and you can start dealing with them, right? So when your wallet is installed in your telephone, say for instance, you can have it on your telephone, tablet, laptop, on personal computer, wherever it is. Okay, everywhere you can install such apps, right? When an app is installed on your telephone and you want to receive, say, a 0.5 Bitcoin as salary from your organization, right? Yeah, they have Bitcoins to pay you. Let us assume the scenario, right? You will ask your wallet, okay, to receive the money. It will immediately generate a secret key and public key pair for you to receive this particular money. Okay, I mean particular bitcoins, right? Secret key will not be revealed. Okay, that will be stored safely in the wallet itself, right? And the public key will be given to the person who want to pay you bitcoins, right? And he will be paying bitcoin to this particular public key as address. Okay, see, in normal GPay or Paytm kind of transactions, your telephone number will be used. Okay, your telephone number can be easily linked to you, right? Whereas in case of bitcoins, the freshly generated public key, which is generated by your wallet, okay, will be used to receive the money, right? So the person who is paying, okay, will not know who the receiver is unless the receiver shows himself up. Okay, if you are receiving your salary from your organization, yeah, definitely your organization knows you, right? But if you are receiving balance from a hotel cash counter, okay, after paying your Bitcoin transaction, okay, you are receiving back some balance. Definitely they will not, they need not know who you are. Okay, all that they will be paying the change is to some random like number which is called as your public key, right? And you receive money through that new public key as your address at that moment, right? And these addresses are all stored in as transactions, and how these transactions are stored will will be seeing them in due course of time, right? And whenever you want to spend this newly received Bitcoin, you have to use your secret key for signing it. Okay, I'll explain how this will look like, but all that you have to understand, to spend this newly received amount, you have to use your secret key for signing it. Once you do a proper valid signature, you can spend it, right? More technical details we'll see. Okay, so your telephone with an app can be called as a node which initiates the transaction in this blockchain network. Okay, and it employs a digital signature, right? Okay, when you initiate a transaction, when you really pay, okay, not while receiving. While receiving, you only make a request to receive, right? Say your hotel man, cashier, or your organization salary paying department, they will be initiating the transaction through their mobile devices or personal computing devices, right? And that node will be signing for whatever Bitcoin it has, okay? And that is a transaction which they initiate in the blockchain network, okay, by employing their digital signature. Am I clear? Okay, there is a chat message for me. Let me see what it is. Sir, can a mobile work as a block? No, mobile cannot work as a block. What is meant by block? I'll explain. Is wallet Is block? No. Wallet is also not a block, but wallet or mobile is a node, okay, which can initiate a transaction or which can receive bitcoins. That's all. Okay, it can be called as a node, right? What are blocks? Where are they stored? I'll explain very shortly. Okay, just wait. But this is really a good question for us to ask now. Yeah. Now PKI, public key infrastructure, manages the public keys and such things. Okay. We'll not worry much about it. We'll restrict our focus to blockchain requirements. Okay. In case of blockchain, all your keys, public keys and secret keys, are managed by your wallet only. Okay. You will not have a different managing tool like PKI. Okay. It's not part of our tools. Okay. I mean, it's not part of our blockchain requirement, right? And also in this public key infrastructure environment, there exists a certifying authority who certifies every public key as this key belongs to so and so organization, right? But such a certification is also not needed in blockchains. Okay, nobody needs to believe who owns or who has the ownership for a particular public key, right? It's only your wallet which takes care of what is your pair of public and secret keys, right? It's not just a single pair. It can generate a new pair for every new transaction that you are going to use to receive new bitcoins, right? For every new inward transaction, your wallet will be generating a new SKPK pair, and with that PK, you will receive money, I mean bitcoins, right? No necessary for any certification or infrastructure managing tools also, right? Blockchain allows key pairs to be generated by user themselves, right? And they are also called as addresses in bitcoins. Because of no central management of public keys, this identity is become okay, pseudonyms. Okay, means they are not something which can be easily related to you as your phone number. Okay, in case of Google Pay, you reveal your phone number. Here, it is not directly related to you. Okay, anonymous. It gives you an anonymous feel, right? Is it really anonymous? Okay, there are research papers again. Okay, those interested can do in this direction also their research. How to break the anonymous character of blockchain networks. Okay, there are many papers which already exist, and still there are many open problems also. Okay, fine. Let me at this now I have not introduced you how this anonymity is given to you, but in due course I'll explain. Yeah. So as I said some time back, your wallet is a node which can generate keys for you, right? And any person who want to pay you will be using your public key, okay, as the address to which he will be paying, okay, and he will be signing the Bitcoin which he owns with his secret key. Is all I said. Okay, but these are all wallets which are in mobile phones, right? Is the connection of such wallets is called Bitcoin network? No, this network has some other kind of nodes. Okay, what are they? They are called full nodes. Okay, or mining nodes, right? What do you mean by mining nodes? These mining nodes really have copy of all transactions being stored in them, right? Starting from the first transaction which Nakamoto created in 2008, transaction that happened till now, every transaction is stored in this full node. Okay, or mining nodes. They are called as mining nodes also, right? So how these transactions are stored in the node? Transactions are stored in block, right? Say for instance, every block stores, say, roughly 1,000 transactions. Okay, it's not exactly 1,000, it's some bigger number. Okay, just for the sake of assumption, we think a block stores 1,000 transactions. Okay, see in your screen you can see block 1, block 2, block 3, and so on. Okay, each block has a header. Okay, header consists of some information followed by body of the block, which contains transactions which are listed there. Okay, transaction 735, transaction B76, transaction 3C2, and so on and so forth in block 1. After some number of transactions, this block gets filled, right? And you store it in the full node, not just one single full node. There are so many full nodes. Every full node will have a copy of block 1, right? And then you start filling block 2, okay, with bunch of transactions for itself. Okay, block 2 again has some roughly 1,000 transactions, but you see in header of block 2, hash value of block 1's header is also stored, right? Similarly, in block 3, bunch of transactions, and in header of block 3, hash value of block 2 header is also stored, right? And also watch, in every header, block header, hash value of transactions in that block are also stored, right? And because of this storing, if you change any transaction, say in block 2, okay, if you change details of any, say for instance, a particular transaction says, your college pays me 0.01 bitcoins for this stock. Okay, your college pays me 0.01 bitcoin for this stock, right? So the transaction is recorded in block 2 for assumption. Okay, say if I have an access to this full nodes and I can change that 0.01 to 0.10, okay, my number of bitcoins that I receive from your college gets increased 10 times. Okay, it's a simple manipulation. But if I do such a manipulation, that will impact the hash value of the transactions in block 2. Okay, so this hash of block 2 gets changed. Okay, once this entry changes, okay, hash value of block 2 header will also change. Okay, so this next block gets changed. I have to manipulate this also. A single change here in a particular transaction of block 2 will change the entries in header of block 2, will also change the values in next block's header. Okay, if there is block 3, that will also have change in its header. Okay, so on and so forth up to the current block. Every header you have to change. Okay, so that makes editing very difficult in blockchains. Okay, some of you might have read this. Okay, blockchain data is immutable, you can't change it. Okay, this is one reason for that, and there are many more serious reasons which I will explain. Okay, but this is how the blocks will look like. Okay, what is meant by uncle block, orphan block, and such things? Okay, we don't worry much about them now. But for block 3, block 2 is parent, and for block 2, block 1 is parent. Okay, for any block n plus 1, block n is its parent, and it is a chain of blocks like this. Okay, and this chain, every full node will have a copy of this complete chain. Okay, such nodes can verify transactions. Okay, and they can collect transactions, new transactions also, right? They can verify them, right? What is meant by verifying a transaction? Whether the signature is valid, okay, and whether the actual person who is paying this bitcoins, he really owns them or not. Okay, Such entire verification can be done by these full nodes because they have record of all previous transactions, right? Okay, after verifying, they'll pool such transactions together and they'll be building new blocks. Okay, how this new block building is done, we'll study in detail. Okay, and this process of building new blocks is called mining. Okay, that's why these full nodes are also called mining nodes, right? Okay. Now let us see what goes into these blocks and its header. This is brief structure of a block, right? So every block consists of this information. First 4 bytes in a block indicates size of that particular block. Okay, size of the block in 4 bytes. Okay, for a new block, first 4 bytes is invariably size of that block, and next 80 bytes is block header. Okay, just now we have seen in our previous screen, every block will have a header. Okay, and this is 80 bytes in size. Okay, and next variable length 1 to 9 bytes gives you the transaction counter, the number of transactions in that particular block, right? And depending on block size, whatever remaining size is left with, that space is for recording all transactions of that block, right? That's why the last row, the size is shown as variable. Okay, block size is not really fixed. First 4 bytes of your block shows you what is the size of this particular block, right? Okay, and header of the block connects these transactions nicely. How this connection happens, we'll see. And headers of subsequent blocks are connected in a chain, as we already discussed. And this chain is nothing but, if you just look back, the chain is nothing but hash of the previous block is stored here. Okay, in the current block. Okay, in block 2, hash of block 1 is stored, block 1's header. Okay, in block 3, hash of block 1's header is, block 2's header is stored, right? In block n plus 1, hash value of block n header will be stored, right? So this hash value acts as the link. Okay, as I said, it's not physical link, but it is linked through this kind of hash value, right? Okay, that's what this says. The headers of subsequent blocks are connected in a chain. Yeah. And 1 second. Sir, how normal computer can be converted to a block? No, computers cannot be converted to block. Block is a data structure which is stored in a computer's hard disk. That's all. Right. And your PC is not enough to store all blocks that started from block 0, Genesis block, which Nakamoto created. The first block is called Genesis block, right? Okay, to the current block. Okay, your hard disk is not big enough to store all this, right? You need a special purpose storage devices and computation devices to become full nodes. Okay, I'll explain why you need so much of computation force also, right? But definitely the number of blocks that were created from 2008, that number is huge number, right? And your storage device is not enough. You need special storage devices for that, right? Okay, computer will not be a block. A computer will consist of, storage device of a computer will store so many blocks. Okay, and it says data structure which has the structure that I have just explained. Okay, am I clear? Okay, so let me come back to talk about the structure of block header. Okay, we already saw that. 1 second. Okay, so we already saw the structure of block, and there we observed that block header is 80 bytes, and this is what is written in those 80 bytes. First 4 bytes, you right version of the software which you are using to create that particular block. Okay, so at the start the version can be version 1, now the version can be any version n.0 and so on and so forth. That version number will be recorded in first 4 bytes. Okay, those of you who use Linux, okay, you know Linux will have various version numbers. Your current version number will be something. Okay, those of you who use Windows, okay, you are using version, your Windows 11 nowadays, okay, is the new version, and many of you might be using Windows 10, right? First 4 bytes of your block header is used to store the version number of software which you are using to create that particular block, right? And next 32 bytes is to store the previous block hash value. Okay, this is actually hash of previous block's header. Okay, if you recall that diagram. Okay, one second. Yeah, you only hash the header of the previous block, not the complete block is hashed, right? Okay, so this is previous block hash, right, which is the hash value of previous block's header, that is 32 bytes. 32 bytes means how many bits? It is 256 bits. Okay, and your hash function that you use in blockchain network, I mean Bitcoin network, is called as SHA-256. Okay, SHA-256, or for that matter any hash function in cryptography, will be dealing with some permutations and some kind of substitution operations, right? What is meant by substitution? Take an input value, substitute that with some fixed one-to-one output value. Okay, what is meant by permutation? Just reorganize your bits into some different order, right? Okay, you repeatedly do this kind of functions. SHA-256 also deals with such functions, but it is such a good hash function which satisfies all our required properties. And SHA-256 gives you 256 bit output. 256 bit means 32 bytes. Okay, so that's why next 32 bytes are for that. And next 32 bytes are for Merkle root. What is meant by Merkle root? I'll explain very shortly, but from your previous blue diagram, okay, I mean this diagram, okay, you see the next important entry in your header is hash of transactions in the current block. Okay, this is your Merkle root. Okay, how Merkle root gives you hash, I'll explain. Okay, but this is Merkle root is nothing but hash of all transactions in the current block. Okay, and next entries are important, but let us see one by one. Okay, next 4 bytes is the timestamp, the approximate time of creation of that particular block, right? And another 4 bytes which is called as difficulty target. Okay, for every block you will be having a changing difficulty target. Okay, and last 4 bytes is nonce. Okay, which is some random number. Okay, and it is also a number which is used to show that you have done some work, which is called as proof of work algorithm. Okay, I'll explain them in my future slides. Okay, this both difficulty target and this nonce are related to each other. Okay, and together they will be giving you proof of work. Okay, what is meant by proof of work? Which is the consensus algorithm used in Bitcoin network, right? What is meant by consensus? Yeah, I'll talk in detail towards the end of my talk, right? Okay, but difficulty target and nonce together will give the required values for achieving consensus in Bitcoin network. Okay, let's continue. Dear organizers, is there any time that I should break? Stop for a while?
Sir, at 3:30, you can go for 5-10 minutes break, sir.
Yeah, please suggest me couple of minutes
Yes,
before so that I can
yes,
stop
sir.
at appropriate time.
Yes, sir.
Okay. Yeah. First, we'll understand how this Merkle tree is constructed. Okay, we have something called Merkle root. Okay, and while talking about Merkle root, I said this is hash value of all transactions in your current block. Right? How your transactions are all hashed. Okay, that is through Merkle tree. Right? Say for example, my block has 4 transactions. Okay, why 4? Okay, sometime back I said 1,000 transactions. Okay, but drawing a tree for 1,000 transactions will make my tree so big. Okay, so it will become difficult for me to explain. Just for sake of simplicity, I'm taking 4 transactions. Okay, so let me call my transactions as A, B, C, D. Right. First, I'll hash each of this transaction. A gives me hash of A, that is H of A. B gives me H of B. C gives me H of C. D gives me H of D. Right. And then I'll take them pairwise. Okay. A and B. I'll concatenate them. Okay. This plus sign here means concatenation. Just write them one after another. HA followed by HB. Okay, they are written together and again hashed. Right. This is hashed value of A and B together. Okay. And similarly, C and D also, H of C and H of D are also concatenated and it's also hashed again. Right. And these hash values are again concatenated and hashed again. Right. So I started with 4 transactions, which gave me 4 nodes of my tree, right? Which are combined into 2 parent nodes, right? And these 2 parent nodes are again combined into one root. Okay, this root of this Merkle tree is called Merkle root, right? And this root as a hash value represents all transactions, all 4 transactions that went into it. Got it? Okay, so any change of any transaction will also have a change in the Merkle root value also. Okay, so this is how all transactions are hashed together to give you Merkle root. Okay, say assume we have 8 transactions. How many different levels you will be needing to go to Merkle root? Okay, I have A, B, C, D, E, F, G, H. E, F, G, H will again give me a similar tree, okay, which has only one, two, three levels, right? 0th level, first level, and second level, 3 levels, right? And those 2 topmost roots of these 2 independent trees can be combined in one more level, and that will combine if all 8 transactions together. Okay, if you have 8 transactions, your height of your Merkle tree is only 3. Okay, here it is 2, right? If you have 8 transactions, it will become 3. Okay, if you have 1,024 transactions, your Merkle tree height will be only 10. Okay, so with a tree of height 10, you can get your Merkle root and you can store the Merkle root, right? But showing it on screen is difficult because I can't show 1,024 leaves. Okay, that's the only difficulty. Am I clear? Okay. But the tree structure is this, right? And this Merkle tree is also used for some particular usage in Bitcoin network. Okay, which we'll talk little later. Okay, now we'll just see how Merkle root is computed and stored in your header. Okay, yeah. So Merkle tree is a binary search tree with its tree nodes linked to one another, okay, using hash pointers, and transactions are organized as Merkle tree, right? And the Merkle root is used to construct the block hash. Okay, hash of all transactions in that block. And if you change any particular transactions, you need to change all subsequent hash values that you see in that Merkle. Okay, say for instance, if I change B, that will change hash of B. That will change of hash of HA plus HB. That will again change the root value, right? So this entire length will be changed. Okay, so I mean, here the height is 2, so I will be changing 2 plus 1 root, 3 values, right? Okay, so any change in one transaction will result in n plus 1, where n is height of your Merkle tree. Okay. But changing 10 hash values, is it so difficult? I can simply change. Okay, can be the thought for any of you. Okay, so changing a transaction here can result in change of 10 hash values and hence Merkle root. Okay, but that changes the hash value of the header itself. Okay, so you have to change the value here, but that changes hash value of that header, and again next block has to change. Okay, as I already explained to you, you have to do so many corrections. Okay, yeah, it just not will be stopping there. It's a bit more complex. I'll explain. So blockchain as an architecture, okay, has different layers. Okay, application layer, your Bitcoin currency, or you may have seen this registration of land or properties in some states are being done using blockchains these days, right? So that can also be an application layer. Okay, various applications you can think of, right? And it can have contract layer, okay, which talks about scripting code. What is meant by scripting code? There are different kinds of blockchains. Okay, what we are talking now is Bitcoin network, which is a permissionless blockchain. What is meant by permissionless? If you have enough money, you can also buy a computing device which have huge computational storage space, and you can become a full node. For that, you don't need you need not get permission from anyone. Okay, all that you have to do, approach another full node and ask for copy of all existing blocks, copy them into your storage device, and you are a full node. Okay, and from then you can also start collecting transactions and pool them into your pool, verify each of them. Okay, all verified transactions will be which are in your pool. Once you have enough number of transactions, you can start creating a new block yourself also. Okay, once you are successful in creating a new block, okay, you will be rewarded. Okay, how this block creation and rewarding is done, I'll explain down the line, right? Okay, but in certain kinds of networks which are called as Ethereum or okay, Hyperledger, okay, different kinds of blockchain networks. Okay, some of them are permissioned blockchains. Yeah, Hyperledger is permissioned blockchain. Okay, so you know, I mean, people simply cannot become a mining node. Okay, you need to be approved by some organization. In fact, Hyperledger organization use it as permission blockchains, and only organization will be allowing certain computers to become full nodes. Okay, no other computer can act as full node in Hyperledger. Okay, so that's the difference. Am I clear? Okay. Incentive layer. Okay, how currency, I mean, how new Bitcoins can be created, how distribution happens and such things. Consensus layer. Okay, what is meant by consensus? Okay, different nodes at different parts of the world are creating new transactions and new blocks. Okay, how all nodes will agree which can be the next block. Okay, okay, and how all nodes will agree whether a transaction is valid or not. Okay, this kind of decisions are called consensus. Okay, it should be agreed by all nodes. Okay, unless that happens, okay, transactions are not really valid, right? So how this agreement is achieved? Okay, in case of Bitcoin network, okay, you see those things are written in black. Okay, Bitcoin network is programmable currency, right? It will not have any contract layer in it. Okay, script code is not really part of it, but certain currency networks also can be used for script coding, like Ethernets. Okay, whereas incentive layer, yeah, is how to create new Bitcoins and such things are part of Bitcoin network, which we will be discussing briefly. Okay, and consensus layer, that's proof of work, which we'll talk about, right? And network layer, okay, it's a peer-to-peer network, and you have a transmission protocol and verification mechanism, right? And data layer deals with data blocks, okay, which we just observed. Okay, we saw something about how blocks are structured, okay, how they are linked together, what's the chain structure between them, and what's meant by timestamp and such things. We have just seen. Okay, hash function, Merkle tree, digital signature, these are all part of your data layer. We completed understanding data layer, not completely, except for some couple of points. Okay, once we are through with them, our understanding of Bitcoin network at overview level will be complete. Okay, but we'll talk about other layers also very briefly. Okay. Yeah. As an application layer, okay, you can see different pictures here. Hyperledger, Ethereum, Bitcoin, MageSafe, Binded, Adapt, Faction, and so on and so forth. Okay, and it's a global ledger where almost in every application you will be having similar chain blocks, right? And the entire thing will be having a peer-to-peer network like this. Some nodes in this network can be full nodes or mining nodes, and some nodes can be just user nodes like your wallets. Okay, but every node is connected together in your peer-to-peer network. Okay, that's true for Bitcoin network also. Okay, we'll be emphasizing till end of my talk only mostly on Bitcoin network. Very rarely we'll be moving on to the other areas. Okay. Yeah. Initially, when a transaction is coming into existence, okay, it will be collected by full nodes, right? And it will be stored in unconfirmed transaction pool. Okay, full nodes will receive new transactions, and those new transactions are stored in unconfirmed transaction pool. At this stage, your transaction is not yet confirmed. Okay, say you went to a hotel and you are paying you for your coffee bill through Bitcoin wallet, some 0.001 Bitcoin, right? Yeah, initially it's a transaction which you initiated, but not yet confirmed. Okay, that is true with your GPay and Paytm also. Okay, once you pay, immediately your transactions are not confirmed. That will take some time. Only once you see tick mark, it's confirmed. In case of Bitcoin network, the confirmation time is little longer. Okay, because of the higher value of Bitcoins, right? Confirmation takes at least 10 minutes, right? And then peers validate these transactions based on some preset criteria and is included in a block, right? I mean, what are various simple points that you can think of for validating transactions? Okay, whatever Bitcoin you are paying should really belong to you. Okay, how will anybody verify that it belongs to you? Just based on your signature, right? And number two, this particular transaction for which you are signing now should be a Bitcoin which you have not yet spent, right? This unspent list will be there with each full node. Okay, they'll also verify the Bitcoin that you are spending now is in that unspent list or not. If it is there, yeah, only then it will allow, right? Okay, so that will stop the double spending. Okay, this is another problem with digital currency where there is no backing by a banking system. Okay, if a bank is there, they will verify whether your account has this much amount or not. Okay, but in case of Bitcoin network, so far I said there is no authoritative system to monitor it. Okay, all full nodes can verify your transaction. That's all. They can't monitor you. And there is nothing like an account where your amount is all summed up. Okay, for different through different transactions, you received some Bitcoins. That's all. Okay, so what is your total sum that you have? Nobody knows, including you. No one knows it. Right? Your wallet can calculate it. Okay, but others cannot do that. Right? But say you want to, I mean, coffee will be taking only 0.001, okay, which you can just take from one previous transaction and spend. Say, for instance, you want to go and buy an apartment. Okay, apartment will be costing you, say, 1 crore, okay, roughly 3 bitcoins. Okay, so your 3 bitcoins you might not have received from a single transactions in previous transactions. Okay, so you might have received your salary, say in 10 different months. Okay, assume your salary is 2 lakhs per month, right? Okay, rupees, right? So it's 20 lakhs in 10 months, right? Which amounts to something around 0.7 bitcoins. Okay, so you have 0.7 bitcoins as an accumulated salary over 10 different transactions. Okay, and you go to someone who can give you loan some number of bitcoins, right? So by looking at your 0.7, this fellow will give you 0.25, I mean 2.5 bitcoins as loan. Okay, so you have 10 plus 1, 11 transactions which gave you this required 3 bitcoins. Am I right? Okay, so you can, a transaction will have some inputs and some outputs. Okay, so the total number of bitcoins that you have is 3.2 because you have 0.7 at your as your salary and 2.5 as the loan that you got. Okay, 3.2 is with you, right? You can list down all those previous transactions with the signature for each of them, right? Because you got them through different transactions, right? So your input is 3.2, your output is just a single transaction which you will be paying to the builder who builds your apartment, 3 bitcoins, right? So what is the balance that is still to be there? 0.2 bitcoins. Okay, what happens to this 0.2 bitcoins? If you don't specify anything, that will automatically become transaction fee to the miner. Okay, I don't want to give 0.2 bitcoins as transaction fee. What I can do, I can generate another public key for myself, and I can receive the balance through that public key. Okay, so to the new address, I'll receive 1.9, I mean 0.19, right? And I'll pay transaction fee 0.01. Okay, so output, there are 3 entries. One entry, 3 bitcoins to the builder. Second entry, 0.19 bitcoins to my own address as balance receiving. And the third entry, 0.01 bitcoins as transaction fee to the miner. Okay, so any transaction will have number of inputs and number of outputs. Okay, this number is not fixed. Okay, it is one or more. Am I clear? Okay, so such transactions are there in unconfirmed transaction pool. Peers validate after verifying signature and unspent balance and such things. They validate the transaction based on the criterion. Okay, peers use computational power to mine for block miners. Okay, I'll explain what is meant by this. Miner nodes need to solve some computational puzzle to publish a block, right? and whoever, what is meant by this puzzle, and we'll see them. Okay, the miners who can solve the puzzle first will become a winner, and his block will become the new block. Okay, that's how he creates a new block, right? A small amount of incentive is given upon successfully creating a new block. Okay, this is extra to the transaction fee that the miner can get. Okay, and in the successful block, there can be 1,000 transactions. Okay, each of this transaction can have some transaction fee. Sum of all those transaction fee will go to the successful miner along with this extra incentive. Am I clear? Okay. And this is the incentive why miners will be working on Bitcoin network to create new blocks. Okay. All these peers in the network then verify the new block using the consensus mechanism. Now, new block will be added to the existing chain, and then transaction is confirmed. Once the transaction goes into the block and block goes into the chain, this transaction is confirmed. Okay, and as per the proved experience so far, if 6 blocks are added on top of your new block, then your transaction cannot be overridden. Okay, it will become secured, right? But confirmation happens as soon as it is added to the chain. Okay, the next block links itself with the new block using the cryptographic hash pointer again, right? Now the block obtains its first confirmation while the transaction obtains the second confirmation. Okay, I mean, the third line says after new block is added and your transaction is confirmed, which is sitting inside that block, the next block which comes after some time, okay, will again be linked to your existing block, the topmost block. Okay, again with the same hash, similar hash pointer, right? And that block gets his first confirmation, and your block, which is just under it, will get second confirmation, right? In general, 6 confirmations in the network is considered as final, I mean secured. Okay, that's what I said. Okay, how does transactions get into blockchain? Okay, transaction is requested by using user wallet. Okay, and then it is authenticated. A block representing that transaction is created, right? The block is sent to every node. Okay, all nodes in the network will receive the block. Okay, nodes validate the transactions of the block and the block itself. Then nodes receive reward for proof of work. Okay, for successfully creating the new block. Okay, they will receive the reward for proof of work. Typically in cryptocurrency, the block is added to the chain of blocks, right? And this updated chain is distributed to the entire network. Then transaction is complete. Okay, so this is roughly the life cycle of a transaction. So from the process, it's clear, it's decentralized. Okay, conventional transaction system versus peer-to-peer transaction system. Okay, this understanding is the understanding of decentralization that goes into Bitcoin network. Okay, see, your network has many full nodes, and each full nodes has copy of all blocks chain, the complete blockchain, right? So this is a completely decentralized same copy of your chain which exists everywhere. Okay, so if you want to manipulate any entry, you have to manipulate the same in all mining nodes. Okay, this is another headache which stops you from manipulating transactions in blockchain. Okay, you have to do the same manipulation at multiple locations. So what is the difference between distributed system and blockchain technology? Yeah, blockchain technology itself is distributed system. Okay, you can't talk about differences, but blockchain technology adds some layers of security to this. Okay, I can't see blockchain technology as something else. It is also a distributed system with some security layers attached to it. Right? Okay.
Sir,
So
sir,
sorry
if
to
we can pause here. Sorry
uh,
to
interrupt you, sir.
Ah.
Can we have a break for 10 minutes, sir?
Yeah, you immediately after this slide.
Okay, sir. Sure. Definitely. Thank you.
Or maybe I can stop now and I can continue from this slide. Okay, I'll stop.
Okay, sir. Okay. Yeah,
We'll
thank
come back, resume after 10 minutes.
you. Yeah. Yeah. So, dear all, as said, let me resume back after 10 minutes.
Hello, am I audible?
Yes, sir, it's audible.
Yeah.
So you may continue, sir.
Yeah. Okay. As we observed, it's a decentralized network. Okay. Persistency okay, is the result of your immutable distributed ledger. Okay, as we already discussed. Okay, editing transactions is so difficult because you have to do multiple editings at many different places, right? And as it is distributed with same copy being present at many places, you have to modify them at different locations. That's also another problem, right? So all these kind of things put together, this becomes nearly impossible to tamper, right? And it provides you anonymity as the transactions are made based on the temporarily generated addresses. Okay, user interacts with a new generated address for each new transaction. This is possible. Okay, it's not necessary. Okay, but possible. Okay, if somebody prefers to use same number for all transactions, same secret key and public key pay, that's also can be done. Okay, it's not ruled out, right? But as a technology, this supports new pair of SKPK for each transaction. So it's really an ad hoc key pair. Okay, so temporarily generated addresses are being used, right? So this provides some kind of anonymity. No guarantee on perfect privacy preservation. Okay, I mean, it doesn't assure you any such guarantee that privacy is preserved. Okay. Excuse me, 1 second. Hello? Yes? Yeah, please, Meher, carry on. Yes. Okay. Yes, go ahead. We will do that, but that will take some time. Okay, how many times can I say this to different students? Okay, every student calls me instead of having me in WhatsApp group, okay, where I can reply to all. I don't know why you guys prefer to call me independently with the same question. Okay, yeah, please pass on this answer to all. Okay, you have to, I mean, this postponement of foundation course will happen. That will take some time. Okay, we cannot do it immediately. Okay, yeah, yeah. Okay, you write if something called not applicable is there, choose that. Okay, if possible do that. Yeah, okay, I'm in a class. Okay, you can't continue to ask me questions like this. Yeah, okay, yeah, okay, okay, right. Yeah. Sorry, participants. Okay, it's a call from another student. Okay, you can, yeah. And auditability, all transactions are recorded with digital timestamp. Okay, and they are permanent, as we saw in above persistent part. Okay, so you can have an audit which can be carried out on these records, and this can be done by anyone. So the transparency is also there. Okay, transparent transactions which can be audited by anyone. So these are the various characteristics or features of your Bitcoin network or blockchain as a technology. Okay, yeah, the different types of blockchains. Okay, as I already explained to you, the public blockchains is what we are talking now about. Bitcoin network, which is a public one, anybody can, is open to anyone. Okay, anyone can read, write, right, and also participant can join the consensus process for decision making. How can you join in Bitcoin network for consensus process? By becoming a full node. Okay, all that you need is enough infrastructure. That's it. Okay, whereas consortium blockchains, okay, is I mean, more than one organization. Okay, multiple organizations come together to form a network. Read permission is open to all within the network, whereas certain constraints are placed on write permissions. Okay, I mean, let us think about this consortium, I mean, land registration network. Okay, each state as an entity is one organization which can have its own blockchain kind of environment where it can record all registration transactions. But you might have seen something in yesterday's budget that Indian government wants centralized registration process. Okay, it can be obtained or it can be achieved by having consortium of blockchains. Okay, each state blockchain can be independent entities. Okay, these organizations can all come together to have a consortium of blockchains, right? And there can be interactions between them. Okay, yeah, how these interactions and what will be stored where, okay, that is again dependent on a particular application. Okay, you have to choose those terms. Okay, what is your data structure, how you are going to plan for your application, and how you are going to deploy rules for making any changes, read, write, and all these things. Okay, they become research topics of making blockchain suitable to a particular application, right? Okay, anyway, coming back to private blockchains are for a particular organization. Say, for instance, Hyperledger is one such. Okay, here read permissions are open to everyone in the network, whereas write permissions are restricted to identified members who can do the writing. Okay, say for instance, if it is about university mark sheets, okay, faculty can have rights to add marks to the chain, whereas students will be given permissions to see the marks. Okay, just as an example. All right. Okay, the same differences, public consortium and private blockchain, are tabulated to explain their differences, right? Consensus determination is done by all miners in public, whereas in consortium or private, it's restricted. Okay, in consortium, it's selected set of nodes, and in private, it's the organization which decides about consensus. Okay, read permissions are public in case of public blockchain, can be public in consortium also. Okay, and similar thing, it can be public in private also. Read permissions. God, 1 second. Hello, మళ్ళీ చేయము క్లాస్లో ఉన్నాం. Okay, immutability is nearly impossible in blockchain, whereas in the remaining two it can be tampered because there are no multiple full domains, I mean full nodes over there. Okay, so your number of copies are limited to certain small number, right? And there it's not proof of work, it's some other mechanism for consensus. So the tampering becomes possible, right? Efficiency in case of public blockchains is very low, whereas the remaining two, it's good enough, high. Okay. And centralization, there is no centralization in public blockchains. In case of consortium, it's partial. In case of private blockchains, it's fully centralized. Okay. Consensus process is permissionless in public blockchains, and it is permissioned in both two other cases. Okay. With these differences understood, we'll continue. We'll continue again with Bitcoin network. Okay. We stopped understanding 2 points of our header structure. Okay, let me just quickly go back to that. Yeah. I don't know why I'm getting so many calls today. Hello? Okay. అసలు ఇంకా నేను ఆమెను తీసుకున్నట్టుగా ఎక్కడ సైన్ చేయలేదండి. ఓకే. DRC1 రుక్మారేఖ పేరు రాసుకోవచ్చు మీరు. ఓకే, దట్స్ బికాస్ వీల్ బి వర్కింగ్ టుగెదర్. నార్మల్లీ మై DRC1 ఇస్ ఆల్వేస్ రుక్మారేఖ. DRC2 ఇంకా ఫిక్స్ చేయలేదు, అది డీన్ సార్ చేయాలి. ఓకే, బట్ అది నేను అప్లికేషన్ ఫామ్ ఇస్తే కానీ డీన్ సార్ చేస్తారు. ఓకే, బట్ ఇంకా నా దగ్గర ఫామ్ రాలేదు. ఐఎమ్ స్టిల్ వెయిటింగ్ ఫర్ హర్. ఓకే, ఎస్. ఆ స్టూడెంట్ని కాంటాక్ట్ చేసి నేను ఫామ్ తీసుకురామని చెప్తాను. ఓకే, రైట్ సార్. Yes. Yeah, we are yet to complete discussion on difficulty target and norms. Okay, this last 2 entries, okay, we are still to discuss. Now we'll quickly understand them also. Right. Say, what's the hash function that we are going to use? As I already said, it is SHA-256. The output size of this is 256 bits. Okay, out of this 256 bits, okay, you can organize them from least significant bit to most significant bit. Okay, so what's the value of least significant bit? It can be 0 or 1. That will be the value of that bit also. Whereas most significant bit, that is 256 bit. Okay, what will be its value? It is 2 to the power 255. Okay, 1 there indicates 2 to the power 255. Okay, I think I don't need not teach you binary number conversion and such things. Okay, but most significant bits value is 2 to the power 255. Right? You agree with me? Okay, fine. D, this difficulty target indicates the number of bits, most significant bits, thus must be 0. Okay, say for instance, the value as such, the output value of SHA-256 is lesser than, always lesser than or equal to 2 to the power 256. Okay, I think this is clear. Okay, when you have 3 bits, right, you can store numbers from 0 to 7. Okay, which is lesser than 8. Okay, that is 2 to the power 3. Okay, you have 256 bits. Okay, so your entire value is lesser than 2 to the power 256 bits. Okay, if I ask 10 most significant bits to become 0, okay, then the value will become 2 to the power 250, I mean, will be lesser than 2 to the power 256 minus 10. You agree with me? Okay, if difficulty target is 10, then the hash value, okay, my condition for the hash value is to see that the complete hash value is lesser than 2 to the power 256 minus 10. Okay, So this D is 2 to the power 256 minus that whatever number of bits that I want to be 0. Okay. This whole number is called difficulty target. Right? So if I increase the number of bits which are to be 0, right? Okay, my difficulty target will become much smaller. Okay. So this will force, okay, only for very few choices of nonce, this hash value will be lesser than the difficulty which I am setting, right? So in the difficulty target, I will be storing the number of bits that must be 0. Okay. If that number becomes greater, okay, this D value will become smaller, right? Okay. So that makes your SHA-256 hash value will be reaching that very rarely, okay, only for few nonces, right? Where nonce is a random number, okay. So the what miner will be doing is miner has all these other values, okay, of the header are fixed, okay, version number, timestamp, previous hash value, all these things are fixed, okay. That is including last hash and transaction part, right? And the only thing that he can change is nonce. Okay, nonce is it is random number. Okay, minor number starts generating various random number for nonces, right? And for each nonce, he will try to compute the SHA-256 hash value, double hashed, okay, hash value, until he reaches a hash value which is lesser than D. Okay, where D is 2 to the power 256 minus the target value which is stored in my 4 bits. Okay, 4 bytes. Right. Okay. So once any miner, whoever achieves the random nonce which successfully satisfies this required condition for hash function, right? That nonce will become a successful nonce. Okay, and that will be written in the header. Okay, and that will become a successful block. Okay, and that block will be communicated to other mining nodes saying that I have achieved success. Right? Got it? Okay, there is a chat question to me. One second. What nonce, sir? Any explanation? Nonce is just a random number. Okay, say I assume I am a miner. Okay, I have last hash transaction. These are all fixed entries of my header, right? I keep changing nonce to different random numbers. Okay, and at some particular random number, my hash value will become lesser than my difficulty target that I have fixed. Right? When I achieve this, that nonce will be a successful nonce which can be written in the header. Okay, that shows that I have worked with various random numbers to get a nonce which satisfies my requirement and hence becomes proof of my work. Am I clear? Okay, so I'll communicate this nonce added header to all blocks. Okay, so each one can verify that this nonce will satisfy the difficulty target. Okay, and when I satisfy it, I will become a successful miner and I will be rewarded with whatever rewards I supposed to get. Okay, which I already explained, right? And the same block will be approved by others by verifying that nonce satisfies the difficulty target, and they'll also add the block with them. Okay, but remember, not just nonce verification, they'll also verify all transactions that go inside the block also. Okay, they'll first verify all transactions. I mean, first verification is done for nonce. Once this is done, they'll verify all transactions, right? And everything about the block will be tallied, and then they'll add that block in their chain, right? Okay, there is something called forks also, which I don't want to discuss now and disturb you people, right? Okay, it can be left for you to read yourself. If there is any question, you can ask me. all participants have to calculate the hash value continuously by using different nonces, which is brute force technique. Once nonce is obtained, miner broadcasts the block to the network and all the nodes will verify. Okay, I have said this everything here. Okay, just for the sake of reconfirmation, I am reading it out. Okay, and after verification, newly created block will be appended to the current blockchain. When multiple nodes find suitable nonces at the same time, okay, I mean, I am working here in India. Okay, somebody in America might also work parallelly with me. Okay, and both of us successfully get nonce at the same point of time, right? So that fellow will propagate his block, and I will be propagating my block to all the entire network, right? So different, I mean, both these blocks are child of same parent node. I mean, same parent block, right? Okay, so nodes which receive these blocks will be receiving them at different time intervals. Okay, some nodes will receive my block first, some nodes will receive the other block first, right? But both will be added to the same parent as children, right? So it is one chain with two children. Okay, that's why it is called fork. Okay, the structure looks like fork, right? How this is dealt with? Okay, because the word anyway we mentioned, we'll also quickly talk about this. All nodes will continue to build the chain. Okay, they'll continue building with the first block that they received as child to the current. Okay, some nodes, as I said, some nodes might have received my block and some other nodes might have received the other block first. Whoever received my block, they'll extend my block, and whichever nodes which received the other block, they'll extend the other block. Okay, like this the network will continue to extend. After some time interval, say after some 3 cycles, okay, they'll verify which branch is longer. Okay, if my block branch is longer, the other branch is truncated. If the other one is longer, my branch is truncated. Okay, and now there is no more fork. It's only one chain. Right? What will happen to the transactions in truncated blocks? They are again sent back to the pools. A transaction pool will again receive them, right? Okay, transactions in fork are not still confirmed. Okay, once one branch is truncated, now whatever is remaining are confirmed. These transactions in the truncated blocks which are not part of any blocks which are already there, okay, they'll all be sent back to the pool of transactions and they are again blocked in new blocks. Got it? Okay, so let me now see what the question is. So what is the proof of personhood? Sir, I am coming across this term for the first time. I don't know what is meant by this. Okay, sorry. Okay, let me check myself and I'll clear it if possible. Okay, at least in the context of blockchains, I have not seen proof of personhood so far. Okay, whatever I know, I'll talk. Anyway, let me see what it means. Okay, we'll talk about this later. Okay, but at the time being, I don't know what it is. Okay. Yeah. So this calculating nonce successfully and then propagating the block to all networks. Okay, this process is called proof of work, right? That proves that some node has successfully mined by guessing the correct nonce which satisfies the required hash function condition. Okay, I mean the required difficulty target for hash function, right? Okay. Please remember, if difficulty target is increased, means if the number of bits that I want to be 0 are increased, okay, that will take more time for mining. Got it? Okay, if difficulty target is increased, okay, I mean the number of bits that are to be 0 are increased, okay, then my nonce is a bit more difficult to search for. Okay, that will increase my required mining time also. Okay, usually the difficulty target is set such that all miners put together can become successful within 10 minutes. Okay, not lesser than 10 minutes. Okay, roughly close to 10 minutes, mining can be successfully done. Okay, that's why I said in Bitcoin network, each block takes 10, each new block take 10 minutes to come into the chain. Okay, every 10 minutes, a new block comes into the chain, right? Okay, that's why a new transaction may also need 10 minutes to get really confirmed. Okay, because it will be confirmed only when it is added into the chain. Got it? Okay, a new block comes into the chain only after every 10 minutes. Okay, why it takes 10 minutes? Because difficulty target is set such that it takes 10 minutes for all miners to become successful, one among them to become successful. Okay, got it. Okay. In proof of work, a chain that becomes longer thereafter is judged as authentic. Okay, I mean, this is what we talked about the fork. Miner receives a block. Creation rewards, I mean, is rewarded with 12.5 bitcoins. Okay, now, okay, but this will be reduced after every 2,10,000 blocks. Okay, okay, this reward is half every 210,000 blocks. Okay, and it reduces to zero after total bitcoin created reach 21 millions. Okay, at this point the miners will get only transaction fee. Okay, this is all about rewards also. Okay, now we almost discussed everything. Okay, Bitcoin block is generated about every 10 minutes, while Ethereum block is generated every 17 seconds. Okay, that's why its the time requirement is much lesser. Okay, miners have to do a lot of computer calculations in proof of work, yet this works waste too much of resources. Okay, you are wasting too much of computation power to do proof of work. Okay, when it's not just one node which tries with various nonces, different full nodes across the world will be trying parallelly with various nonces to successfully get a nonce which can show proof of work. Okay, so it is wastage of so much of computation power, right? So people started disliking proof of work for this reason. Okay, that's why other consensus algorithms come into role play. Okay, some consensus algorithm I'll discuss in my lecture. Okay, one was suggested by one of the participant, proof of personhood. Okay, I'll try and find it out what it is. Okay, right now I don't know. Okay, to mitigate the loss, some proof of work protocol design some side applications also. Okay, like prime coin. Okay, it started searching for prime number chains. Okay, where these prime numbers can be used for other mathematical research areas. Okay, such various tools are also there. Okay, but we will not venture into it. As such, Bitcoin does only proof of work that we discussed. Okay, good. Okay, now the emphasis moves on to consensus algorithms, but after talking a bit about scripting languages. Okay, how transactions are written. Okay, transaction has the structure of which I have already discussed: list of inputs, list of outputs. List of inputs gives you all input entries. I mean, the number of bitcoins that you are going to spend now are resultant of some previous transactions. Okay, these inputs will be listing those previous transactions along with signatures, right? List of outputs gives you the output entries through which you are paying through this transaction, right? Okay, so an input has to be signed for valid expenditure from that, right? Okay, how this signing is recorded in Bitcoin network, we'll understand now through the scripting language. And after this, we'll talk about some consensus algorithms. Okay, anyway, let me continue. Okay, to explain scripting language, okay, I have taken a small example where I have used numerical values to demonstrate. Okay, you can see, and to evaluate scripting language, we will be taking help of a stack. Okay, initially the stack will be empty, right? And the script, which consists of constants and some functions, okay, will be processed. Okay, this script has some number of constants and two functions. Okay, let me first read it. 2, 3, add 5 equal. 2, 3, 5 are constants, add 5, add and equal are some operations, right? Okay, when you see a constant, that is just pushed onto the stack. When you see an operation, okay, operation needs some number of operands. Those many operands are pulled from the stack, operation is performed, and the result is pushed back to the stack. Okay, that's what I do. Okay, so 2 is a constant, so it is just pushed onto the stack. Then 3 is also a constant, it is also pushed onto the stack, right? Next, add is an operation. Add needs two numbers to be added up, right? So 2 values from the stack are popped, right? Okay, 2 and 3 both are popped out, they are added. 2 plus 3 is 5, that is written back to the stack. Now see, stack has only entry 5 there. Okay, and then you move to the next entry in your script, which is 5, which is also a constant. So just push down to the stack, right? And then you go to the last entry, which is equality checking. Okay, so you need 2 values to check for their equality. So pop 2 values from the stack, 5 and 5, they are equal. So true is written to the stack. Okay, so this is how scripting language is processed. Okay, now we will see what happens in Bitcoin network. Okay, Bitcoin network has 2 components, locking script and unlocking script. Okay, when you receive money, locking script becomes entry of your transaction, which is recorded in the block, right? Which has these values. Okay, dupe is an operation, duplication. Okay, it just duplicates the entry in the stack. Okay, makes a copy of the topmost entry. That's all. Okay, duplication is an operation. Hash 160, right? Of the public key. Hash 160 is again operation. Okay, it's a hash function, right? Which you can perform. Okay, followed by hash of the public key is stored. Okay, public key is also not directly stored here. Okay, hash of the public key is stored, right? And equality verification, that is equality checking, is next operation. And check signature, signature checking is the last operation. Okay, these things are stored. Okay, just in this order. Okay, duplication, hash 160 as a function, hash value of the public key, okay, to which the amount bitcoins is received. Okay, this hash value is stored, equality verification, check signature. And when somebody wants to spend bitcoin that he got from the transaction, all that he will be doing is unlocking script he has to send it. Okay, which consists of signature, which he makes using his secret key, right? And the public key, the complete public key is sent now. Okay, while spending that amount. Okay, this public key and secret key are there in the wallet of the person. Okay, so his wallet will be doing the signature, and his wallet will also send the public key, right? So this unlocking script and locking script together will become the script for verification, right? So how this is done? Signature is pushed down to the stack, and then public key is pushed down to the stack. Public key is duplicated and it is hashed. Okay, so now at this point the stack will have signature, public key, and hash value of the public key. Okay, and then hash value of the public key, which is there already stored in part of locking script, is pushed into the stack. and then equality checking is done for two hash values which are there on the top entries of the stack. If both hash values, okay, the hash value which was just computed and hash value which is already stored in the transaction that went into the block, right? If they match, then you continue to the next. Okay, if it is false, this stops here. Okay, if it is matched value, then check the signature with both the public key and signature which are already stored there in the stack. Okay, if it also tallies, then you continue, you validate the spending of the particular input. Okay, this is how the scripting language is used for processing inputs of a transaction. Am I right? Okay. Okay, the same thing. Just now I have explained this. You are seeing the same thing in a diagram. Okay, good. So, independent verification of transaction. Each node verifies every transaction against a long checklist of criteria. Okay, you can see the list. I have been talking about this list in my talk for the past 1 or 2 hours. Okay, I don't want to again reread the whole stuff. I just leave it for you to read. Okay, every transaction, syntax and data structure, everything is checked for. Okay, it's a long list of entries which are necessary for validating a transaction and a block also. Okay, so proof of work we already discussed. I don't know why this slide got duplicated. Just during the talk, I received this from one of my students. Okay, I must thank my student Anita who made this presentation for me. Okay, yeah, these are all slides which we discussed. And validating a new block. The block data structure is syntactically valid. Okay, I mean, what's the block data structure? It should have a header with these components, and before the header, it must have size of the block, and followed by list of transactions. Okay, and so everything should be correct, right? And block header hash is lesser than the target. Okay, and then the proof of work. Okay, with nonce which is already part there, the entire header when it is hashed must give you lesser than the difficulty target which is already written in the header itself. Okay, this proof of work has to be first verified, and then timestamp is verified. Okay, it should be lesser than 2 hours in some future time. Okay, I mean, when you are in 4 o'clock of what is today's date, 2nd February, okay, your timestamp cannot be showing sometime which is in future 8 o'clock of 2nd February. Okay, it can be at the most 6 o'clock on 2nd February. Okay, and with today's date, right? So it can go at most 2 hours in future. Okay, why you allow 2 hours in future? Because different nodes may have different running timings. Okay, so you allow some variation. Okay, but it can't be too long, right? Okay. Block size is within acceptable limits. The first transaction, the only, I mean, first transaction is coin-based transaction, and only first transaction is coin-based transaction. What is meant by coin-based? That is the reward which the successful miner will be getting. Okay, as soon as I successfully mine it, I will be rewarding myself with 12.5 bitcoins. These bitcoins are newly created, right? This is how new currency is created in Bitcoin network. Okay, this is the currency creation rule in Bitcoin network, right? So first transaction of every block is coin-based transaction, and only that first transaction is coin-based network, right? Okay. Yeah. So let me very quickly, I will not be going in this detail about the topics that I'm going to talk now. Okay. I'll very quickly talk about consensus. What is meant by consensus algorithm? Okay, and I list various consensus algorithms that blockchains use. Okay, and my list is not exhaustive. Okay, it's only an indicative list, right? So before doing that, let me talk a bit about what is meant by consensus. So let me first introduce to you something called two generals problem. Okay, what is this two generals problem? Say, yeah, definitely. I know I'm talking to a bunch of people who are from Hyderabad or its surroundings, right? Is there any participant who comes from non-Telangana region? Okay. Any participant who comes from non-Telangana region, please say yes in chat. Okay. So no reply so far. So I assume there is no one. Do you know how Telangana got merged into India? There is an event called police action which took place somewhere around 1950s. Okay, and during that action, Indian Army invaded Nizam government. Okay, which is called as Nizam in that period, from three different directions. Okay, one is from the direction of Aurangabad, and the other is from the direction of Gulbarga, okay, which is called as, which is part of Karnataka nowadays. Okay, and the other is from the direction of AP, okay, Warangal or Vijayawada. Okay, three different directions with three different armies. The Nizam territory was invaded. Okay, and because of this multiple directional invasion, Telangana lost in no time. I mean, Nizam lost his fight in no time. Okay, almost some at the most 5 days. Okay, I don't remember exactly. Okay, at the most 5 days, the Nizam lost the war and he surrendered to Indian Army. Okay, that's what happened in history, right? Why these three different armies? Multiple armies will add to your strength, okay, and can make your opponent weaker, right? But this adding strength will happen only if they attack at same time. Okay, if three different armies come at three different time frames, okay, Nizam would have easily won the war also. Okay, we don't know, right? Because if it is a single army which comes from in any one direction, Nizam might have won it, might have destroyed it completely, right? If second army comes after a week, he would destroy that also. If third army comes after a week of that, okay, that army might have also be destroyed, right? Indian army won the war because they attacked Nizam simultaneously. Okay, so that is very important. So here we talk about two different armies want to attack a city and they want to agree on some time. Okay, say the message is attack on Monday at 10 p.m. Right? Army A has a general, let us call General A. Army B has General B. Okay, General A sends a message to General B with the attack date and time, right? And General B acknowledges it, right? On receiving the acknowledgement, they will both attack the city at the designated date and time, right? But is this a successful, a good approach? Is this a good approach? Where can be the problem? Okay. Some messenger takes the message from General A to general B, right? If he goes and conveys the message to B, then he acknowledges it. Okay, again the messenger comes back to general A and passes on the acknowledgement to him, right? Once he receives the acknowledgement, okay, we said they can attack at designated date and time. But you see, there can be a problem. Okay, while taking this acknowledgement back, okay, if the messenger gets caught in the city or by the forces of the city, right? General A might not receive the acknowledgement, so he will not attack. Only army B will be carrying on with the attack, right? So the simultaneous attack principle is lost, right? Okay, because General B thinks he has sent the acknowledgement. Okay, General A not yet received the acknowledgement, so there is some flaw. So this fellow stopped in participating in the attack, whereas General B, who forwarded the acknowledgement, goes on with the attack. Okay, so it's a problem. How it can be resolved? You can ask for a second acknowledgement. Okay, again General A re-acknowledges to General B. Okay, but the problem will again continue. Okay, okay, while taking the second acknowledgement, if the messenger gets caught, General A will be going on with the attack, General B will be still waiting. Okay, you can add any number of acknowledgements. This two generals problem cannot be solved with a real successful acceptance. Got it? Okay, two general problem is unsolvable with this kind of approach, right? Is there any way you can reach consensus in this general problem? Okay, two general problem might not be just only for armies and generals. Okay, you can remodel it for two PCs also. You need to run some distributed algorithm. Okay, so first PC sends some parameters to second PC, right? Okay, but the computation has to happen simultaneously. Okay, so you don't know whether the second PC receives it or not. Okay, so until you get an acknowledgement back. Okay, so ask for an acknowledgement, right? But you don't know whether the acknowledgement reaches the first PC or not. Okay, it might get lost in the transition. Okay, so planning for parallel execution of both the systems might be a difficult thing. Okay, so what you normally do, you normally think of some number of acknowledgements, and with that threshold you stop. Okay, once you receive, you continue, and you assume it's going to work, right? Okay, now we extend this to a three general problem. Okay, and it's also Byzantine three general problem. What is meant by Byzantine three general problem? Okay, it is similar to two general problem, but here you have a third general also. By saying Byzantine, it means one among the general can be corrupt also, or can commit mistakes. Okay, at a random phase. Okay, one among the three generals can come mistakes randomly. Yeah, Byzantine is fault. Okay, yes. Byzantine three general means, yeah, one among the three generals can be faulty. Right. Right. Yeah. Even Byzantine three general problem have the similar issues that we discuss with two general problem. Okay, if one among the three generals can be Byzantine, even this problem has some difficulty in solving it. Okay, Whereas when you go to 4 generals, okay, you can easily see a solution. Right. This is Byzantine 4 generals problem. Right. First general sends to second and third, I mean both to all 3 remaining 3 generals some value V. Okay, one sends V to the remaining 3 generals, right? And P2, okay, this yellow marked one is a faulty one. Okay, I have not discussed the 3 general problem in detail. Okay, from this diagram you can carry out that idea. Okay, you can look back into it. But now this 4 general I will be discussing in detail. Okay, the value that commander P1 sent to the remaining 3 generals is V, right? Okay, 2 sends V again to 3, but 3 is the faulty one. Okay, 3 communicates U to 2, right? Okay, and 2 also communicates V to 4, right? And the same V will be communicated, which 4 also received V from 1, right? Okay, that will be sent to 2. Okay, so in both directions you see V here, right? Similarly, from 4 to 3 there is a V which goes, but from 3 to 4 you will be having a W. Okay, this 3 is a faulty guy. Okay, he communicates wrong values to both 2 and 4, right? So one which sends V is fixed to V, whereas 2 receives 2 V's and a U. Okay, the majority that is received by P2 is V, right? Similarly at P4, you can see the majority is V. Okay, it gets a V from P2 and a V from P1 also, right? So majority here is also V, whereas this fellow is faulty. We need not worry about it, right? When you have 4 generals, just by looking at majority rule, okay, these 3 generals can come to an agreement, right? Okay, so that becomes the consensus with 4 general problem, Byzantine 4 general problem, right? Just by looking at majority. Okay, even if commander is faulty, okay, still you can come to an agreement with 4 general problem just by looking at majority. Okay, these people can fix a value for themselves and they can communicate and come to an agreement with majority rule, right? Okay, you can just read the diagram with that labels on the edges. Okay, that will make it evident, right? So Byzantine 4 general problem has a solution, but not Byzantine 3 general problem. Okay, a 2 general problem even in non-Byzantine case has no solution. Got it? Okay. So based on this kind of logic, okay, Paxos was a consensus algorithm which was a fault tolerant agreement, right? Paxos lets all nodes to agree on the same value despite node failure. Some node, okay, as here it's a Byzantine general problem where a general can be faulty, right? Some nodes can also be faulty, okay, so which can result because of node failure or network failure or any delays, right? Still Paxos can lead to an agreement, right? And it's an extremely useful consensus algorithm, okay, almost on the lines of general problem. Okay, it also looks at the majority rule. Nodes agree that X is the primary, okay, and okay, I mean, who can be the leader? Okay, among the nodes, who can be the leader? Okay, just based on the majority, you can come to an agreement that X is the primary node from the existing nodes. Okay, such a thing can be easily agreement can be reached, even when there are possibilities of faulty nodes or node failures. Okay. And I don't want to deviate much on this. Right. Let me come back to blockchains. Okay. Because we are already at 440. Yeah. Different consensus algorithms. Okay, 1 second. There's a chat question. What is commanded here, sir? Where? 1 second. I think the question is about this kind of thing. One among the generals can be seen as commander. That's all. Okay. The person or the general who initiates the communication is seen as commander. Fine. Yeah. In Byzantine 4 general, okay, the general who initiates the communication, okay, I'm calling him as commander, right? Okay, fine. Okay, Paxos and draft are close to each other, but anyway, because I'm not really trying to spend time on that. Okay, yeah. Proof of stake is yet another consensus algorithm where the node which has higher stakes, okay, say for instance, okay, this is used in Ethereum also. Okay, Ethereum has something called Ethereum gas, right? The node which has higher amount of Ethereum gas, or which can spend higher amount of Ethereum gas on the block mining, can be the winner, right? Okay, that's why it's called proof of stake. Okay, proof of stake requires people to prove the ownership of the amount of currency or whatever it is. Okay, it need not be currency always. In case of Ethereum, it is Ethereum gas, right? Okay, many blockchains adapt proof of work at the beginning, but slowly they transform to proof of stakes. Right, Ethereum is also one such. Okay, Ethereum initially started with proof of work only when it is called as EP hash, and slowly it moved on to Casper, where it is now using proof of stake. Okay, to combine the benefits of proof of work and proof of stake, proof of activity is proposed. Okay, a mined block needs to be signed by n miners to be valid. Owner of 50% of all coins exists, he or she cannot control the creation of new blocks on his or her own. Okay. More, the nodes with higher stakes will be participating in mining, right? And this process needs signing of at least n miners, okay, some threshold number of miners to be valid, right? But again, to stop somebody taking the edge over everyone, okay, owner of 50% of all coins, okay, there are some 10 lakhs coins assume, okay, if somebody owns 5 lakhs coins by himself, okay, then he or she should not be participating in the process of decision making, okay, so that can lead to problem. Proof of capacity, who has the larger drive space, who had the larger computation power, okay, they will become the decision maker, right? Yeah, this is yet another consensus approach, okay, but this will not be suitable for Bitcoin networks. Okay, proof of importance, there can be different participants, right? Like say for instance, if you talk about your college, okay, principal, there can be head of the departments, there can be faculty, there can be students. Each person will be having different importance. Okay, among this importance, whoever are competing, higher importance can gain value. Okay, you call it priority or whatever it is. Okay, that's proof of importance, proof of storage, proof of deposit. Okay, you can ask nodes to deposit something. Whoever can deposit higher value can become the successful bidder. Okay, so that's where you can call it as proof of deposit. Delegated proof of stakes. Okay, there can be different stakes which are owned by different nodes. Okay, a node can delegate its proof, I mean its stakes to someone else, so that the receiver will have higher stakes. Okay, such thing is also possible. Okay. Okay. Practical Byzantine fault tolerance. Because anyway. And in tomorrow's session, okay, you may receive more discussion on these topics by Dr. N. Rukmareka, who will also be talking about the same values. Okay, anyway, proof of work, proof of stakes, proof of Byzantine fault tolerance, okay, a delegated proof of stakes and tendermint. Okay, these are various consensus algorithms, right? And identity management of nodes is open with respect to the three of this. Okay, proof of work and proof of stake and delegated proof of stakes. Okay, proof of fault tolerant Byzantine fault tolerance. Okay, it's permissioned. Okay, for identity management. Okay, it is permissioned. This is also permission. Right? They are not open. Right? As I said, Bitcoin, there is no management involved. Okay, it's just open. The same thing is true for networks with proof of stakes and delegated proof of stakes also. But networks which use this consensus, okay, it is permission, right? In a similar way, you can see various aspects and the differences between them with respect to various consensus algorithms here, right? I think I don't want to discuss them in detail. Okay, I can end this presentation here, and if there is any time left for me.
Yes, sir. Hello.
Yeah.
Yes, there are 15 more minutes, sir. If the audience are having any queries, they can ask.
Yeah. I don't know whether okay, let me see if there are any questions. I'll first answer them. Okay. What I thought I'll spend a bit on elliptic curve digital signature algorithm. Okay. But I feel 15 minutes is too short for me to handle. Okay.
So, yeah, dear audience, do you have any queries regarding this topic?
If there are any questions, I'll answer them. Okay, and one second. First, let me see if there is a need for me to talk about public key cryptography and such things. Okay, I thought they are known to the people. If there are no questions, I can ask a question and I can answer the same.
Okay, sir. I guess there is no response from the audience. You can go ahead with that, sir.
Yeah. So, okay, I'll take a topic which I can definitely finish in 15 minutes. We talked about two kinds of nodes. Okay, one an user node and the other one the full node, which is mining node. Okay, user node has no blocks or no transactions stored with it except its own secret and public keys, right? Whereas the full node has all transactions which are pulled into blocks, and blocks are all chained together, and the complete chain is with every full node, right? Say I got 1 Bitcoin from some transaction A. Okay, now I want to pay to some vendor 0.5 Bitcoin. Okay, so I'll sign using the transaction A's secret key, right? And I'll bring in that 1 Bitcoin as input entry for my current transaction, right? So any node which want to validate my transaction has to first check that the transaction A and signature there are valid. Okay, signature can be verified using the scripting language that I have just explained, right? But even for that, okay, even for that, you need to get the transaction A from that existing block, right? Okay, how can, I can even supply the transaction A, that locking signature also to the vendor. Okay, both unlocking signature and locking signature, my wallet can submit to the vendor, right? Okay, with the reference to transaction A, right? But transaction A there is in block N, right? Before validating my signature or everything, first verification that the vendor has to do is existence of transaction A in block N. Okay, how can he do that? Vendor is again a simple user like me. I can't expect vendor to have a full node and the complete storage of all blocks and such things. Okay, so he will not have such storage with him. Got it? You agree with me? Participants, do you agree with me? Vendor will not have copy of all blocks, but vendor has to first satisfy himself that my previous transaction A, which I was referring to in my input values, is existent in block N, where I am claiming that it is there. Okay, first he has to satisfy that. How can he do that? Can anyone suggest me? I am claiming my transaction A was there in block N. How will vendor verify that? Hashing less T. No. Hashing will not come here. Any guess? Any hint? Okay. So one possibility is he can send my transactions to the nearest full node and ask the full node to confirm whether the transaction is there in block N or not. Isn't it? Okay, that can be one immediate approach. Okay, that can be one immediate approach. He can send the full transaction, the transaction that I have just referred to, transaction A, and I also said it is there in from block N, right? The transaction number. Okay, so he can just send it to the full node. Full node can look at block N, and it can go into the transactions of block N and see that the transaction is there or not. If it is there, it can confirm, right? But here he has to believe what that full node says. Okay, there is a need of trust, right? Okay, but we always think in Bitcoin network, no node trusts any other node. Okay, there is no trust between them. Okay, it is all an untrusted environment. Okay, so the sending of full transaction and asking for its existence in a block is not going to be happening. Okay, I'll use Merkle tree for achieving this also. Okay, how I'll do that? I'll not send the transaction as it is to the node. Instead, I'll send some reference numbers of the transaction. Okay, just by using which it can search for transaction in its block. Okay, right. And I'll say what it will do. 1 second. Let me again share my presentation. 1 second. Yeah. Okay, this is more relevant for me. Okay. Say, assume my transaction is B. Okay. Okay. I started with A, right? Okay. Assume my transaction is A. I'll send reference number of A from which block that full node can detect the transaction and its block, right? And it can recreate this Merkle tree. Okay, because it has the complete block with it, it can recreate the Merkle tree, right? Okay, please remember, I am not sending it the complete transaction also. I am only sending it's some reference pointers which can point to A, that's all, right? From there it got A and it got the block and it can create this Merkle tree, right? And what it will send me back is H of B, okay, which is the pairing value of A, right? From the parent node of this, another pairing value is H of HC plus HD, right? Okay, and the Merkle root. It will send me these three pairing values, right? It will send me H of B. It will not send anything about A. It will send me H of B. It will send me H of C plus H of D and the Merkle root, right? On receiving that, what I can do is I can hash my own transaction A, which is there with the verifying node, right? It is called special verifying nodes or simple verifying nodes, right? Okay, I mean my vendor, okay, he can just hash the A, the transaction which I gave him. He'll get computing hash value of A, H of A, right? He can concatenate these two and hash it again. So he will get the parent node. This pairing node, H of C plus H of D, was sent by the full node, right? So he can again concatenate them and rehash it. So he will be computing the root himself, right? And he also received a root from the full node. He will compare these two values. If they both match, okay, then it automatically proves that the A is there in block N. Okay, now he need not believe anyone. Okay, just from the values, the Merkle root, this H of C plus H of D and H of B that he received from the full node, he can prove himself that A is there in block N. Okay, without believing anyone. Okay, there is a chat message. Let me see. How can blockchain technology useful to general public other than cryptocurrency? Yeah, I just said you can use it for any application that you can think of, starting from land registrations to logistic verification, okay, logistic recording, okay, everything, whatever you think of, okay. Say for instance, for medical applications or for issuing certificates for a university. Okay, anything, any application that you can think of, you can use blockchain to keep the record of that application. Right. Say, let me say one point here. Okay, when computers came into existence, when I was quite young, okay, so when I was in 10th standard or so, people in India started seeing computers. Okay, then there was a feeling that computer can solve every problem on this earth. Okay, but later people started continue to use computers, but they solve no problem. Okay, every problem remained as it is, but they just changed what is current stance and research of India in blockchain technology. Let me comment about this. Okay, 1 second. Okay, but later people realized, yeah, computers can help them to solve problems. It will not solve problems by itself. Okay, and blockchains nowadays is seen as a technology which can solve everything on this earth. Okay, again, let me say, it will not solve anything. It will only be a good tool which can help you to solve many problems. Okay, what is the research status? Yeah, as a technology it is available, but when you want to think about an application, say for instance, I say you want to use it for certificate issuing in your university. Okay, then you need to think about appropriate data structures and appropriate cryptographic tools which will help you to achieve that task. Okay, you have to modify the given explained blockchain technology that I have explained for Bitcoin technique now. Okay, it will not be suitable as it is. You have to modify it or you have to tweak it to suit your application. Okay, so any application area is still a research area in not only in India, in every other country. Okay, blockchain technology is not yet matured enough to be applied in different domains. Okay, for any domain you have to tweak it to suit to that domain. Okay, that brings in various research problems. Okay, so not just this, not just application areas, many security aspects of blockchain are also research topics. Okay, in Rukmareka, tomorrow's speaker will be explaining to you on various security aspects of security and privacy aspects of blockchain, which are again good research topics. Okay. Making blockchains suitable for different applications, yeah, is a good research topics in different applications that you can think of, right? And various security and privacy aspects of blockchain are also different research directions which you can think of. Right, I think I have answered your question. Is there anything else, sir? Who asked this? Okay, thanks. Right. Okay, any more questions? If there are any more questions, I can answer, or else I'll end the session. Okay. Sending these nodes, root along with the pairing nodes up to A, is called Merkle Path. Okay, this Merkle Path can be used by simple verification nodes to verify existence of a transaction in a block without actually transmitting the whole block from the full node to the verifier, or transforming or transmitting the transaction from the verifying node to the full node. Okay, you need not transfer anything. Instead, you just transfer some bunch of hash values. Okay, that is enough to prove that a transaction is existing there in a particular block, right? Okay, this kind of proof is good enough to satisfy yourself about existence of a transaction in a block. Okay, and this process is called proof using Merkle path. Right. Okay, I think I'll end my talk here. If there are any questions, I'll quickly answer. view.
Yeah. Dear participants, are there any queries from your end? So let us end today's session.
Let me
Thank you
one
so
second,
much.
ma'am. One
Yes, sir.
second. One
Yes,
second.
yes. Please, please.
Let me thank the person who is interacting with me. Okay, I don't know what's his name. Okay, I think his full name is Gausuddin something.
Okay.
Okay, I first thank him for constant interaction. Okay, you made my talk a bit lively. Okay, thanks, sir. Okay, yeah, now you can continue, ma'am.
Yes, sir. Thank you. Yes, sir. Thank you so much, sir. It was extremely informative. You have started with the basics, like how, like you came across the evolution of blockchain. Then you have discussed about building blocks of blockchain, and then you have moved into the nitty-gritty details of each and every concept, which is there, which is almost related to this. So the session was really a valuable session. We are looking forward to have many more sessions in this way, sir. Uh, yeah, thank you so much once again, sir. Thank you, audience. Looking forward to meet you all in tomorrow's session at 2 p.m. with a new topic on security and privacy on blockchain by Dr. Rukma Beka, Associate Professor, University of Hyderabad, engaging more people and on a greater level. Stay safe, stay healthy, and be productive. Have a wonderful day. Thank you. Sandeep, I guess we have shared the link, right? Share the link for feedback as well as Q&A.
Yes, ma'am.
Yeah.
Yes, ma'am. Both I have shared
Hello,
feedback and quizzes.
shall I leave the
It will be
meeting?
open till 7:30.
Yes, sir. Thank you so much, sir.
Hmm. Okay, I'm leaving the meeting.
Yes.
హలో చెప్పండి అమ్మా నాగమణి చెప్పమ్మా